Hello everyone, welcome to my channel. I'm Joe. Today let's talk about the binary arithmetics. And let's start with unsigned binary numbers. So for unsigned binary, which means all the bits from a minus 1 to a left m, all these bits will be used to calculate the magnitude of that number. And there's only positive number. That's unsigned number. Okay. So for unsigned binary number, the addition operation is almost the same as the regular arithmetics, excepting we are using binary number. So there are only limited possibilities. Like we have 0 plus 0 equal to 0. But I put 2 bits here because we know in addition we have the sum bit and also we have the carry bit, right? So that's why I put it as 2 bit. So sum bit and carry bit. Then 0 plus 1, 0, 1. Carry bit is 0, but the sum bit is 1. 1 plus 1, because this is decimal, this is binary, as we talked before, you have to carry to the next bit when you reach 2. So 1 plus 1 actually in binary equal to 1, 0. Okay, 1 plus 1 plus 1 equal to 1, 1. Okay, once you got this idea, you can do the unsigned binary addition very easily. For example, we have exercise here 1, 0, 0, 1, 0 plus 1, 0, 1, 0. So 0 plus 0, we get 0. 1 plus 1 should equal to 1, 0, because we have to carry to the next bit. So 0 plus 0 plus is carried 1, so we get 1. 0 plus 1, we get 1. 1, get 1. So we can do a verification. So 1, 0, 0, 1, 0. That's actually 18. 1, 0, 1, 0. That's 10. So 18 plus 10, we should get 28. Let's verify this. So this is 16 plus 8 plus 4. That's 28. So that's addition. For subtraction, it's similar. So we have 0 minus 0 equal to 0, 1 minus 0 equal to 1, 1 minus 1 equal to 0, 1, 0 minus 1. 1, 0 basically is decimal 2, right? So 2 minus 1 should equal to 1. And here one thing is that because the LSB, which is 0, is not enough to minus 1, so it borrows from the higher bit, and when it borrows 1 from higher bit, it gets 2 on this bit, so 2 minus 1 gets 1, and this borrowed away, so it becomes 0. Okay, so let's try with this 1, 1, 1, 0 minus 1, 0, 0, 1. Try 0 minus 1 is not enough. It's not enough for you to borrow from next bit. Become 2. This becomes 0. So 2 minus 1 you get 1. 0 minus 0 you get 0. 1 minus 0 you get 1. 1 you get 0. Okay. Also we can use decimal number to verify this. 1, 1, 1, 0. That's 14. 1, 0, 0, 1. That's 9. 1, 0, 1. That's 5. So correct. There are 2 more practice problems, so let's try them out. So 1, 0, 1, 1, 1 plus 1, 0, 0, 1, 0. 0 plus 1, 1, 1, 1 equal to 1, 0. You should carry 1. 1 plus 0 plus 1. Again, you should carry to the next bit. 0 plus 0 plus 1, get 1. 1 plus 1, get 0, 1. Okay, verify it. So this is 23 plus this is 18. So the answer should be 41. Let's try this. So you got 32 plus 8 plus 1. That's 41. Okay, so correct. Then 1, 0, 0, 0, 0 minus 1, 0, 1. So you need to borrow, need to borrow, right? So you got 2 here, 2 minus 1 equal 1. You left 1 here, so it's 1. You left 1 here, that's 0. Left 1 here, 1, it's become 0. Verified, so this is 16, this is 5. 16 minus 5 should be 11. 1, 0, 1, 1, that's 11. For multiplication, similar way as in decimal numbers. Okay, so let's try this. 1, 1, 1, 1 by 1, 1, 0, 1. Think about how we do multiplication in decimal number. So we use the first bit to multiply the first number, right? The multiplicand. So 1 multiply 1, 1, 1, 1, we get 1, 1, 1, 1. Then we use the second bit to multiply the first number, the multiplicand. And but the result, we should also shift to the left by 1 bit. But 0 by anything, you get 0 basically. Then the third bit to multiply the first number. So we get 1, 1, 1, 1. Don't forget to shift the last bit. 1, 1, 1, 1. Finally, we can add all of them together. So we get 1, we get 1, 1 plus 1. Excuse me. I carry 1 here. So 1 plus 1 plus 1 plus 1. So basically I get 2, 0. So you need to carry 2 here. So 1 plus 1, you get a 0. And carry 2, you still get a 0. And you carry 2 here. So 1 plus 1, 0. 0 plus 2, you need to carry 2 here too. So 1 plus 2, you get a 1, 1. Again, let's verify quickly. So this is 15. This is 13. So 15 by 13, let's calculate it. 45, 15, that's 195. Let's verify this. So this 7, 2 to the power of 7, plus 2 to the power of 6, plus 2 to the power of 1, plus 2 to the power of 0. So which is 128 plus 64 plus 2 plus 1. So we get 195. That's correct. So for division, we also use same way as we treated decimal numbers. So we write the dividend here and the divisor here. Then we first, because the divisor is 4-bit, so we look at the first 4-bit of the dividend. 1001 is smaller than 1011, so we can't do the division here. We need to add another bit, so 10010. So if we put 1 here, 1011, then do the subtraction, we get 1 here, 0, get 1 here, 1 here, 0. Then move the next bit down, so 1110, so we can put 1 here, 1011. This is 1. This is 1. This is 0, 0, 0. So 110 is not enough, so we need to put 1 here, put 0 here, and put the next bit down. Okay, then I put 1 here, so 1011. Get 0, 1, 0, 0, 0, 0. Okay, so basically we get the quotient equal to 1101, and we have remainder. which is 1, 0. Now let's talk about signed binary numbers. We know that in decimal number system we use the plus sign and the minus sign in front of the number to represent the sign of it, right? But in binary numbers we don't use those symbols. Instead we add an extra bit, which is the S bit, to represent this sign. 0 means positive, 1 means negative, and the rest bits is called the magnitude bits. Okay. And they are used to calculate the magnitude of that number. And the S bit determines it's negative or positive. And another important thing about signed number is that when we're talking about signed binary, we have to specify how many bits we are talking about. Without that information, we don't know which bit is the signed bit. Okay. For example, let's don't do that. Let's say 27. Let's write 27. We can write 27 in 8-bit binary. Like 27 by magnitude is 16 plus 8 plus 3, right? So this is 27. Then we add it up to 8-bit. We add 3-bit here. So this is 27 in 8-bit, but also we can write it in 6-bit. Okay. So here we know only the highest bit. The 8th bit is the sign bit, but in this case, the 6th bit is the sign bit. Okay, this is matter when we do that operation. To represent negative binary number, we have several ways. First, we can use the true magnitude form. This is the most common form that people will think of when talking about negative number. It's the same. Basically, we use same representation as positive numbers, except to change the sign bit to 1. Okay. For example, let's write positive 57 and the negative 57 to 8-bit binary. Let's see what will happen. So 57 equal to 32 plus 16. That's 48. So we need another 9. So 1, 0, 0, 1. Okay. Put it to 8-bit. So for positive 57, we got 0, 0, 1, 1, 1, 0, 0, 1. Naturally, we will think we just change the sign bit. So 1, 0, 1, 1, 1, 0, 0, 1. This will represent negative 57. The second way is using 1's complement form. So in this form, the positive number is not changed. So we still have 0, 0, 1, 1, 1, 0, 0, 1. Okay. But for the negative number, we use a different way. What we do is subtract the positive number from the binary number consisting of all ones. So here we need using a number with all ones, so 8 ones, because 8-bit, minus the positive number. Okay, if we do that, get 0, 1, 1, 0, 0, 0, 1, 1. So basically you can see that every bit of the positive number is changed to the opposite value. Okay, so in this case, this one represents negative 57. The third way is using 2's complement form. So for 2's complement form, the positive number still no change. For negative number, we just need to find its 1's complement first. So using this number to subtract the positive number, again we got the number where all the bit is flipped. Then we use this number to add 1. So we get 1 1 1 0 0 0 1 1. So now in 2's complement, this number represents lective 57. So you must wonder why we have those three different ways to represent the same lective number, and they look different. Here is why. Let's try to do some calculation using those 3 ways we just talked about. Okay. Say, because in decimal we know that we have a positive number minus another positive number is equivalent to a positive number plus a negative number, right? Make sense? Now let's verify if this is true in the side binary numbers by the 3 ways. Okay, first, true magnitude form. Let's try to do the calculation for the left part. So 80, again, let's say we just use 8-bit. Okay, side number. So 8 is 64 plus 16. So this is 80, positive 80. Then we minus positive 65. Positive 65 is 0, 1, 0, 1, 0, 0, 0, 1. Oh no, 1, 0. This is 0. Okay. Then we do the calculation. So this is 1, 1, 1, 1. This becomes 0, 0, 0, 0. So the result, this is decimal 15. Correct, right? Now let's check the right. So if we do positive 80 plus negative 65, see what we will get. Then how do we represent negative 65 in true magnitude? That's 1, 1, 0, 0, 0, 0, 0, 1. So let's do the calculation. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Immediately we can tell this is totally messed up. It's some weird number, but it's not the answer, right? So that's why in the computer system we don't use true magnitude form. Okay, now let's check the 1's complement form. The left side actually exactly same as this, because the positive number will not change. Now just for the right part, let's see. So 80 is still 0, 1, 0, 1, 0, 0, 0, 0, plus. Now negative 65 is by flipping every bit of positive 65, right? So we get 1, 0, 1, 1, 1, 1, 1, 0. Let's add them together. So 0, 1, 1, 1, 0. Carry 1 here. 0, carry 1 here. 0, carry 1 here. 0, carry 1 here. So if we can take this one out, because we only have 8-bit. So we see the result is 1, 1, 1, 0. So it's closer to the true result. It's 14, but missing 1, right? Now come to the 2's complement. The left side, positive minus positive, still the same, no change. But for the right side, we got 80, positive 80, plus negative 65 in 2's complement form, which is 1, 0, 1, 1, 1, 1, 1, 1, because the 2's complement is equal to 1's complement plus 1, right? So now let's do it. 1, 1, 1, 1, 0, 0, 0, 0, 1. Take this one out. We don't need that bit. So now see, now you can see the result is correct. Now the question comes, why do we have to do this? The reason is that in the hardware, computer hardware, like in the ALU, arithmetic and the logical unit, which handles all the arithmetic operation and the logic operation, okay, there's only hardware or circuit for addition. People don't desire a specific subtraction circuit there because it makes the circuit more complicated, it costs more money. Okay, since we can do subtraction using addition, so there's no need for the specific subtraction circuit there. So that's why in all computer systems, we always use 2's complement form to represent negative binary numbers. Remember this. In general, this signed binary arithmetic is still simple enough, except you must remember one big rule here. So in order to do signed number operation, the two operands must have the same number of magnitude bit, same number of magnitude bit. Okay, this is critical. You must satisfy this, or you cannot do the operation at all. One example is here. You can check by yourself. This is totally wrong answer here, but you cannot do that. You must make sure the two operands have the same number of bits. So as long as you can make sure the two operands have the same number of bits, the addition is no difference from the unsigned number. Okay. There are some limitation we will talk in the next lecture, but now let's focus on how to do the signed binary arithmetics. Basically, I already showed you how we do it. We do the subtraction using addition instead. So basically what I'm trying to say is how the computer do the operation. For human, we have no problem. We can using positive number minus positive number, or we can also using like positive number plus negative number. Doesn't matter for us, but it matters for the computer system. So here we'll try to use the way the computer look at it. Okay. So if we wanted to calculate 65 minus 80, instead the computer will calculate 65 plus negative 80. So to do that, we need to first find the binary number for 65, positive 65. If we still use 8-bit, we will get 0, 1, 0, 0, 0, 0, 0, 1. That's positive 65. Then for negative 80, what do we get? For positive 80, we will get 0, 1, 0, 1, 0, 0, 0, 0. So put 80, then the negative 80 should be represented by the 2's complement of this, which is 1, 0, 1, 0, 1, 1, 1, 1 plus 1, which is 0, 0, 0, 0, 1, 1, 0, 1. So 65 minus 80 equal to this plus this 1, 0, 1, 1, 0, 0, 0, 0. Okay, if we do the calculation, 1, 0, 0, 0, 1, 1, 1, 1. Okay, so this is actually the result. And we know that in decimal this should result in negative 15. So how do we verify that this is equal to negative 15 or not? Be careful. The result we get here, if we check the highest, the MSB, remember what's that bit? Because we are talking about signed binary here, so the highest bit, the S bit, actually represents the psi. So this 1 here basically tells us that this is a negative number, and this negative number is represented in the 2's complement form. So this is the 2's complement form. Then the problem is how to find the magnitude of this negative number. How to find the magnitude. So the trick is that to verify it, you need to do the 2's complement of this number to find out their magnitude. So here's how we verify our result. So first we take 1's complement again, then we add by 1. So you can see this binary number, this is a positive binary number, and its magnitude is 15. So which means the magnitude of this number is 15, but it's a negative number, so this equal to negative 15. Basically, this is the correct answer. You got it? Okay, so we will talk more about the arithmetics in next lecture, and that's for today. Thank you. So again, if you think this is helpful, please like, share, and subscribe. Thank you.